Okay, let's turn to problem set 3, which should be quick. So there are 3 questions about a Battle of Sexes game. So that's a coordination game, and we should expect 2 Nash equilibria. Let's play it quickly. So we have 2 players, Mary and Sammy, and they can either agree to go to the opera or to the stadium. So if Mary thinks that Sammy goes to the opera, shall Mary go to the opera or the stadium? So we compare this 2 to that 0. And of course 2 is better than 0, so we underscore this one. And if Mary thinks Sammy goes to the stadium, then Mary must decide, shall I go to the opera and get 0, or go to the stadium and get 1. 1 is better than 0, so we underscore the 1. Now we play the game for Sammy. If Sammy thinks Mary goes to the opera, shall he go to the opera or to the stadium? So now we compare a 1 with a 0. Of course the 1 is better. And lastly, if Sammy thinks that Mary goes to the stadium, shall he go to the opera or to the stadium? So we compare the 0 to the 2, and 2 is of course better. So as expected, we have 2 Nash equilibria. There is no social optimum, but the players do have individual preferences. Obviously, Mary would prefer to be with Sammy in the opera. Sammy would prefer to be with Mary in the stadium. So first question, the Nash equilibrium is opera for Mary, stadium for Sammy? No. Stadium for Mary, opera for Sammy? No. Both opera for Mary and opera for Sammy, and stadium for Mary and stadium for Sammy are Nash equilibria, so the correct answer is C. Which of the following statements is true? Sammy always prefers stadium to opera. That's actually not true, because Sammy would prefer the opera to the stadium when he can go to the opera with Mary. Likewise, Mary always prefers opera to the stadium. No, she rather goes to the stadium as long as Sammy is there too. C, as long as Sammy and Mary are together, neither one matters where they are. That's not true, because Sammy would like to be with Mary in the stadium and Mary would like to be with Sammy in the opera. So in this case, none of the above is true. If the game were played sequentially and Sammy chose first, what would be the Nash equilibrium of the game? Okay, so we can draw that. So in this case, Sammy would have to decide, so let's make a decision node. And Sammy has to decide, shall I go to the opera or shall I go to the stadium? Well, technically, if Sammy makes that decision, then he needs to basically wait. So that's a chance node. What happens next? And Mary could decide to go also to the opera or to the stadium. And if Sammy first decides to go to the stadium, he needs to wait to see if Mary would go to the opera or to the stadium. Okay, so now for each outcome, what is Sammy's payoff? Let's put here Sammy. And to the next, Mary. Well, in the opera, what does Sammy get? He gets only 1. How much does Mary get? Opera, Mary gets 2. Then opera stadium, so Sammy goes to the opera and Mary would go to the stadium. So opera, stadium, either one gets 0. And if Sammy decides to go to the stadium and Mary decides to go to the opera, it's the same. So stadium, opera, everyone gets 0. And lastly, if Sammy goes to the stadium and Mary also goes to the stadium, so then Sammy gets 2, Mary gets 1. Okay, so now Sammy can use backward induction because he knows if Mary is given that Sammy goes to the opera, if she goes to the opera, well, she gets 2, and if she goes to the stadium, she would get 0. So in this case, we can actually eliminate this branch. This is not going to happen. Then Sammy also knows if he goes to the stadium and Mary would go to the opera, then Mary would get 0 as opposed to going to the stadium where she gets 1. She can also eliminate this one. So now the only thing that Sammy needs to decide, under which decision tree do I get the highest payoff, and that is obviously with stadium. So that reduces the 2 Nash equilibria to 1. So the question is, if the game were played sequentially and Sammy chooses first, what would be the Nash equilibrium of the game? And that is stadium, stadium, as we have just seen. Okay, so that was a quick problem set, but let's just stop here and then continue with the next one in the next video.